Hey folks, welcome back and welcome to our online students. The last time we got together, we did electron configurations and orbital notations. The electron configurations was this 1s2, 2s2, 3p6 sort of stuff. And then the orbital notation or orbital diagrams is where we had the boxes and we put the arrows going up and down. And so that was a little bit of practice. Today what I want to do is do a little bit of practice, but then also show you some weird stuff that happens when we get into the transition elements. And oftentimes, if you take chemistry in high school, they talk about the transition elements. They're kind of a thing, but they kind of gloss over it because the transition elements do some weird stuff. And so today what we're going to do is we're going to take a look at electron configurations, orbital notations, and then some of the weird stuff that happens in the d orbital. Now to get us started, we're going to take a look at a couple of elements. We're going to take a look at chromium and copper. And so to get us started with chromium and copper, I'm going to start out with the electron configurations, then we'll do the orbital notation. So I'm going to start out here with chromium, Cr, and then copper, Cu. And for my electron configurations, if you find these elements on our periodic table, and we find chromium up, see where element number 24 is on your periodic table? Chromium. Okay, so we're going to do our electron configurations for chromium, and we're going to go left to right. Just going to go left to right. And so we start out with chromium, and we go 1s2. That gets us to helium. And then we go to 2s2. And that gets us to beryllium. And then we start out with boron, 2p6, and that gets us to neon. And then we have 3s2, that gets us to magnesium. And then we start at aluminum here, that'll be 3p6. That takes us from aluminum over to argon. And then we're going to start out with 4s2. That gets us to calcium, and then chromium's 4 spots over. And so is that going to be 4D? No. Oh, good. That'll be 3D, how much? 4. Okay, 3D4. All right. Now, I'm just going to leave that for right now, and I'm going to do the same thing here with copper. And we can see that copper is element number 29. So all of this would be the same for copper. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right, and that would be for copper. Now, all of this is our electron configurations, and we can shorten this. We have shorthand for this because doing all of these core electrons is kind of a pain. That's a lot of stuff there, okay? And so we can shorten all of that. So we can take all of this stuff right here, all of that stuff right there. These are our core electrons that are not involved in chemical bonding, and we can shorthand all of that, and we can call that argon. So we could call this bracket argon like this, and then go 4s2, 3d4. And for copper, we could go argon 4s2, 3d9. Okay. Now I hope nobody's writing in pen because we're going to make some changes here in just a hot second. Okay. Any questions on the electron configurations? All right, now we're going to do the orbital diagrams for this. Now the orbital diagrams, we're just going to look here at our valence electrons. So I'm going to do 4s and 3d. So I'm going to go 4s, it says 2 there, and then I have 3d4. And I'm going to make some boxes here, so put my box like that. And then the d orbital, how many boxes do I make for the d orbital? 5, yeah, excellent. So 5 boxes. Let's see if I can count these right. I've made mistakes on counting boxes and making periodic tables. It's happened. Watch the video from Friday. Okay. All right, so there's my boxes there for chromium. And for copper, I'll do the same thing. I'm just going to write it down below here. I'll go 4s2, and then I'll do 3d9. And I'll make my boxes here like this and like this. Okay, 1, 2, 3, 4, 5. Okay. And then I'm going to put my electrons in. Now this 4s2 orbital, and I hope you're not writing in pen, I'm going to put in 2 electrons. 1, 2. Okay. And then here for 3d4, I'm going to follow Hund's rule. Hund's rule says we like to go left to right. We like to put one arrow in a box at a time, and we want to have similar spins. So I'm going to go left to right. I'm going to go 1, 2, 3, 4, like that. And at that point, I pat myself on the back, and I'm feeling pretty good. I'm like, okay, I've done my electron configuration. I've done my orbital notation. I followed Hund's rule. Everything is good. Everything is awesome. Everything is awesome when you're part of a team, except when it isn't. And it turns out the transition elements just decide they want to do their own thing because they're special like that. And so here's the thing. These d orbitals are more stable if they're either half filled or completely filled. They'll be more stable. Also, we've learned earlier that the 4s and the 3d are very close in energy levels. Very close in energy levels. And because of that, we can swap electrons. And what will end up happening is we're going to end up losing an electron from the 4s, and it's going to drop over here to the 3d. Notice that this is 4, this is 3. 4 is bigger than 3. So we can drop from a higher energy level down to a lower energy level like this. And now that makes our orbital notation here half filled. All of these electrons have the same spins. See that? Okay, and so we should change this here. We should change our electron configurations. This should be a 1, and then this here should be a 5. You see that? A little magic there. Now, as we take a look at copper, copper would be like this, 2 in the s orbital, and then 9 here in the d, the 3d. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you see where I'm going with this? If you had to make a prediction, could you make a prediction for me? Based off of what you just saw happen here with chromium to make it more stable, what do you think is going to happen with copper? Yeah, we're just going to take one from here, and we're going to drop it down into the 3d orbital. This becomes 4s1, and this becomes 3d10. Yeah, okay, and that makes it more stable. Now, the question is, how do you know which elements will do this? Which elements are going to steal from the s orbital and drop electrons down into the d orbital? Which elements are going to do that? Well, if we look at our periodic table and you find chromium, you see chromium there is element number 24. It's 4 over, and it'll steal 1 so that it'll be similar to Mn. Mn. That's manganese, not Minnesodium. Okay. Hey, don't laugh. I get neon and nitrogen mixed up. Y'all should have been here on Friday. It was a disaster. Okay. All right, so chromium, molybdenum, and tungsten. So Cr, Mo, and W. W is actually wolfram, but it's tungsten. Okay, so those elements will steal 1 from the s. And as we take a look at copper, there's copper, which is in the 9th element from the left there, 9th element in the d orbital. Copper will do it, silver and gold. Copper, silver, and gold. They will each steal an electron to have a completely filled d orbital. So those are the only elements that will do this. Okay? So just in the 4th spot over and then in the 9th spot over. So that way we could end up with 5 or 10 electrons. Any questions on that? Okay. So now, let me throw something else at you here. Oh, wait a minute. Okay, totally makes sense now. Now, monatomic ions. Monatomic ions are when you have a single atom and we have gained or lost electrons to make an ion. Now, typically what we're going to be doing looking at metals is we're going to be losing electrons, so these will be positive ions, or we'll call these cations. So if positively charged, we call this here a cation. If it's negatively charged, we call it an anion. And so we're going to be gaining or losing electrons to make this happen. Gaining or losing electrons to make this happen. Monoatomic ions. And an example of this is we take a look at our periodic table and we find sodium. Sodium is over here in the very first group, and sodium has 1 valence electron. If it loses that 1 valence electron, then it becomes similar to a Nobel gas. And so if we take a look at sodium, it has 11 protons, 11 neutrons in a neutral atom. If it loses that 1 electron, it becomes similar then to neon. Neon is a Nobel gas. And so it'll be much more stable. So it loses 1 electron, becomes a cation. And if we take a look at, say, fluorine, fluorine is way over here on our right-hand side of our periodic table. It's element number 9. If fluorine were to gain just 1 more electron, it would also have a Nobel gas configuration and be more stable. And so it forms a -1 ion. Now, on your periodic tables, what I would encourage you to do is I would take that first column, the hydrogen, lithium, sodium, potassium, rubidium, and at the top of that column, I would write a +1. Because we know those elements will form +1 cations. And then if we take a look at beryllium, this is the second column there, the second column, group 2, beryllium, magnesium, calcium, strontium, those would all form +2, okay? +2 cations. And then if we migrate over a little bit further and we find boron, boron and aluminum and gallium, those will form +3. Now when we get below gallium, it gets a little weird, but for boron anyway, boron, aluminum, and gallium, it'll be +3. And then let's move all the way over to the right to fluorine, chlorine, bromine, iodine, okay, or halogens. Fluorine, chlorine, bromine, iodine. That column would be -1, so I'd label that -1. Oxygen, sulfur, selenium, that would be -2. Nitrogen and phosphorus, -3. And then now we've got carbon. What would carbon be? Plus or -4? Yeah, it swings both ways, right? So carbon could be a plus or a -4. Plus or -4. And how would we know what it is? It's going to depend on what it's combined with. And we'll take a look at that as time goes on. Okay, so those are going to be our ions there. This is a good thing to have written on your periodic table. Now, when we get to these main group elements, and we start taking a look at, the transition elements, we're going to see that we remove electrons from the highest energy level. Okay, so maybe this is like a note to ourselves here. Note to self, when making ions, remove electrons. Electrons might be 1, might be several electrons. from highest energy level first. Okay, always remove from the highest energy level first. So that is to say we'll remove electrons from the 4s before we would remove them from the 3d. Okay. And now, just so you know, copper tends to form a +1 cation in nature. This is what it does. Now, when we take a look at our orbital diagrams here, can you see an electron that might get lost? Which one would it be? The 4s. So we would take this electron here. This electron here would go, it's in the highest energy level. That makes this a 0. And that gives us our copper with a +1 cation. Okay, I'll go, oh, I see that. I see that. Chromium also does a +1. Which one would it lose? The 4s. Okay, here we are. Okay, and it kind of makes sense. Now, if I were to take a look at a couple of others, let's take a look at iron. Iron Fe will make a 3+ and a 2+. Fe 2+. It does two different cations. And that's a little bit of a head scratcher. You go, what? What's going on with that? Okay, so if we did the electron configurations for iron, we find iron up there in our periodic table. It's element number 26. And I'm going to do the kind of the shorthand here. So I'm going to go argon. I'm going to go argon like this. Okay, and I'll go 4s2, 3d, 3d, 1, 2, 3, 4, 5, 6. 6, like this. Okay. And so this will be the same thing here. I'm going to go argon like this, 4s2, 3d6, like that. And then I'm going to do my orbital notation. So I'm going to do my 4s and my 3d. I'm just going to do this over to the side here. I'm going to go 4s and then 3d. Okay, 4s and then 3d. And then I've got a 2 and a 6 and a 2 and a 6. And I'm going to make my boxes here like this. 1, 2, 3, 4, 5. And like this. 1, 2, 3, 4, 5. Okay. And then I put my arrows in. And oh, here. Oh, you wore a hat today. Thank you. Help me out here. Two. Up and down. Okay, so up and down. Yep, excellent, thank you. Okay, and then I've got 6 here. So up and down. We're good? Oh, next one, up, okay. Up, up, okay. So let me count. 1, 2, 3, 4, 5, 6. Nicely done, nicely done. Okay, and this would be the same. Okay, like this. Okay, like that. Okay, well done. All right, now, if we're going to make a 2+ cation, we're going to lose 2 electrons. Where are they going to come from? Highest energy level. Yep, okay. So we're going to lose from here. Those go away, and this becomes 4s0. Okay. And then iron also makes a 3+. So 3+, well, okay, we're going to take away 2 electrons here, like that. And then one more electron, it comes from the d orbital, which one? The down one, right? One of these 6 is not like the other. One of these 6 is not quite the same. Y'all need to watch more Sesame Street. Did you ever watch the Sesame Street episode where Big Bird explains quantum mechanics? No? Did you ever watch Sesame Street? Well, that's why. Okay, all right. Okay, so now this explains, oh, wait a minute, 5 here. 5. So this explains why iron will make a 2 plus and a 3 plus cation. It's like, oh, that's how that works. We have to look at the orbital notation for that to make sense.